Hello, am I audible?
Yes, ma'am.
Okay, so welcome to week 9 of the tutorial session on foundations of cryptography. So let me share my screen and then we will proceed. Is my screen visible?
Yes, ma'am.
Okay, so let us start with the okay, before that, I think I remember last week we had some confusion about the Merkle tree question. So, how many nodes are there in a Merkle tree where we have 1024 data nodes? That was the question. And the answer was 2 to the power 11, right? So, I think I was already explaining that thing. So, let me just repeat that thing once again, and then I will start with this week assignments. So okay, I will just write here in this slide only. And, okay, so this is last week doubt. Okay, so we had Merkle tree with 1024 nodes, right? So if we consider a smaller example with 4 nodes, so what happens is that we have 4 data nodes, right? One, hello, anyone is saying something? So we have 4 data nodes, right? And what we do is that they are all leaf nodes. So at the last level, or at the last level, we have 4 nodes, right? They are all data node. And now what we do, we hash the content of this node here and content of this node here, right? So this stores the hash of the left child, this part stores the hash of the right child, and we concatenate the data here in this node, and same goes for here also, right? Now uh, then again in this level, so this becomes 2 nodes, okay, and in this level again this left half stores the hash of the content of whole left child, right? That is concatenation of two hash values, and we hash the whole of it and store it here in the left half, and similarly the right half stores the hash of this whole thing, right? So now we have one node, right? One node, and note that this node has two hash values in it, right? But we need to hash the whole content, so this concatenation of these two hash value gets again hashed and gets stored in another like final root node, right? And this contains the total hash of both of these values, right? So this is the final root node, which is again adding extra one node to it, right? So till this point, this 1 plus 2 plus 4, this is 7, and due to this final node, final one node, it becomes 8. So for 4 data nodes, we have 8 node in the Merkle tree. With the same logic, with 1024 data nodes, that is 2 to the power 10, we have 2 to the power 11 nodes in the Merkle tree. So that is how we resolve this question, okay? I hope that makes sense. Okay. Also, I remember there was this problem 1 that we discussed last week. I think the question was that how ciphertext integrity is not provided by uh, MAC then encrypt approach. So this is one part, okay? So last week doubt 1, okay? And another thing, just let me discuss it here. So as we know, to build authenticated encryption scheme, we have necessarily three approaches, right? One is encrypt then MAC, which always gives a secure authenticated encryption scheme provided that the underlying encryption scheme is CPA secure, and the MAC that we are using is a strong MAC, right? And then there is this encrypt and MAC approach, which is also not necessarily secure, and it depends upon how we instantiate the MAC protocol, right? So this is not always not leading to authenticated encryption scheme. And the last one is MAC then encrypt, right? So in MAC then encrypt, what happens is that we first compute the tag of a given message. So let's say we compute the I am writing MAC for the tag generation algorithm with the key of the MAC scheme. So for message M, we first compute the tag, and then we apply the encryption algorithm with respect to encryption key upon the concatenation of both message and tag values, and this gives the final ciphertext. This is how the encryption is done in MAC and MAC then encrypt approach, right? Or authenticate then encrypt, I should say, right? Authenticate then encrypt. Okay. Now in this approach, we were saying that ciphertext integrity is not provided, and the reason of saying is that here the tag, so authentication or integrity, right? So that is provided by the MAC part. Okay, message authentication code ensures the authenticity and integrity of the message. Now this tag is computed on the message. However, when the final ciphertext is getting computed, there is no authentication provided on the final ciphertext, right? So you can forge the ciphertext and it will go undetected, because the tag is computed on the plain text. When in the receiver end you decrypt this ciphertext, you get M concatenated with the tag, and then you check whether this tag is a valid tag for this message, and that checking only ensures the integrity of the underlying message. But what about this whole ciphertext C, if at all it is a valid ciphertext or not? If when getting communicated, if you change the C to some C dash, you cannot check that with this underlying MAC, because underlying MAC only ensures the authenticity of this plain text, this tag corresponding to this message M, but no tag is there corresponding to this ciphertext C. That is why we say that ciphertext integrity is not provided by the authenticate then encrypt approach. Okay, so these two things I just had to recap from last week. Now
one question in this, but
Yes.
but if we change in this, if we change the ciphertext, then anyways it will be a meaningless meaningless message. It will not decipher properly, so the receiver is going to decryption oracle will throw an error. So anyways,
So you
the way the motive of attacker is not met.
the motive of attacker, you are talking in terms of the exact game for ciphertext integrity.
Yes.
So you were correct that, like, in a very broad view, it is like it is not maybe always possible, but you can't even say that it is impossible to change the ciphertext in a way such that when you decrypt, so it depends completely upon which encryption scheme you are using. So your encryption scheme was said to be CPA secure, it was not CCA secure, right? So a CPA secure encryption scheme can lead to malleable ciphertext. What do we mean by malleable ciphertext? Such that C can be changed to C dash in such a way that underlying message has some meaningful, like it is indeed a valid ciphertext for some message. Say the message got decrypted to some M dash concatenated with T dash, but there is always a probability that t dash turned out to be a valid tag for m dash also, and it did not get discarded by the receiver. There is this probability. You cannot completely discard this value because this encryption scheme is just said to be CPA secure, not CCA secure. So this ciphertext can be malleable, and this ciphertext can be tweaked in such a manner that the underlying it is not an invalid ciphertext. It got some value such that this t dash became some tag for some m dash. Okay, does this make sense?
Yes, ma'am, but because when we say that we go one step ahead and we say that the T dash and M dash are a proper pair, it means we are questioning our MAC algorithm.
Right. So also one thing here that I was already mentioning, that this check whether t dash is a valid tag for m dash or not, this check is completely corresponding to the integrity of m dash. Okay, but the here basically c is a ciphertext for m concatenated with t, only this part. So when you are
Yes.
checking the ciphertext integrity game, you will be satisfied if you are able to come up with some C dash which gets decrypted to some valid string which is m dash t dash. Now next part, whether t dash is a valid tag for m dash or not, that is not your concern right now, because this encryption scheme overall, right, the ciphertext integrity game will try to come up with a ciphertext C dash which is a valid ciphertext of some m dash t dash which is unknown to the unseen to the adversary previously, according to the ciphertext integrity game. And then you are done. The next part, whether t dash is valid tag for m dash or not, that is a different issue, right? So just focusing on the ciphertext integrity game, for this encryption scheme, it is enough to be to make the ciphertext tweak in such a manner that it gets decrypted to some valid message, right?
Okay, ma'am. Ma'am, one question
Yes.
was related to this only. Now there was a question in the assignment also, similar question. So there I had marked, I think when you discuss the assignment, then I can ask that question. It was similar M concatenated with T. So maybe
Okay,
at that time.
okay, I will come to that probably if this
Yes.
is this
Okay.
week's assignment. Okay.
Yeah. Thank you, ma'am.
Okay. So okay, let's start with this the last week's assignment. Select the correct options. Padding oracle attack is based on the error response sent by the receiver. Okay, let's go one by one. So this is true or false?
This is true.
This is true, right? Because in padding oracle attack, we basically see from the receiver's end whether it led to a padding error or not. So that is the error response sent by the receiver, and by exploiting that error response, we are able to basically eventually retrieve the whole padding part. So how many padding bytes were there, and then even after that the rest of the message bytes also, right? So okay, so first statement is true.
Ma'am, one question in this. So I understood that part when we say that in the padding oracle attack, the padding is the attacker can retrieve the padding part. I
Yes.
understood that and how it does.
Mm-hmm.
But when we talk about the attacker can retrieve the remaining text also, so that is more like a hit and trial method, right? There is no other method for that.
Yes, but still, because it is a byte, right, and byte value can be just between 0 to 255, so it is not taking some exponential time. It will take like 256 times you try and error. That is possible to do in a real world, or in a
No, but
practical attack.
if the block size is more, it's not a 1 byte. If the block size is 16 bytes,
So
then
you get 16 into 256 times. tie. So
16 into
like
2.
if there are
Yes, 16 into 2, 56. Yes.
yes, so you are targeting one byte each time you are targeting one byte. Once that byte is recovered, then you target the left the byte left to it. So one after another you try, and eventually at max, at the worst scenario, I am saying 256 try, because even before that you are trying with each possible byte value. So you will not require 256 byte checking each time. You will need much less than that. So upper bounded by 16 into 256 in that case, which is still possible to do.
So basically, it is a number of times the attacker will be able to.
Yes, if
That is less.
right, you need the access to padding oracle, so that many times the adversary is allowed to access the padding oracle. So you are
So
exploiting the padding error only.
yes, yeah, understood that. And so basically, till the time that padding byte is reached, not reached, the adversary will get a padding error. Otherwise, the adversary will get like something like a deserialization error, right? When the
Yes.
adversary is trying to extract the text,
Mm-hmm.
then we'll get the deserialization error.
Yes, so the way you are observing the error, that is how you are like the method as described in the lecture also, how you are retrieving the message bytes. First, how
Okay.
many bytes are padded, that is one part, and then you are doing this try and error thing with the while retrieving the message byte.
Okay. Got it.
Okay, so second statement is one-way trapdoor functions have same security properties as one-way function. So okay, let me just tell you. Last week, I think someone asked in some other form in the chat. So what I understood from the question is that the underlying security of one-way function and one-way trapdoor function, they are same or not. So according to that, I remember I answered that they are same. However, the way this question is constructed in this question, so it essentially says that whether they are exactly similar, which is not right. So one way trapdoor function, you have this extra trapdoor information with you, which you can utilize in some application. So it is completely upon the application where you want to use, whether you want to use the one way function or you want to use one way trapdoor function. In case of one way function, you don't want anyone to get in the reverse direction and get back the input. In one way trapdoor function, the security says that without the information of trapdoor, it is hard for an adversary to get back the corresponding x value. Given a random y value from the output space, it is hard for an adversary to get the corresponding x value such that fx equal to y. In when you are not eligible to get the value of the trapdoor, but if you are a eligible one who has the trapdoor access, then you are able to go back in the reverse direction. So in terms of that, they have different security property. Okay, so I don't know, like I think like I did not see this week's assignment last week actually. So I did not get exactly, maybe you were trying to ask the answer for the question. So okay, I hope this makes sense that that statement that one-way trapdoor functions have same security properties as one-way function, this is wrong, because the security game of one-way function and security game of one-way trapdoor function, they are different, but the underlying one-way property, that is same. Okay, the only difference is that in one case you have the extra trapdoor information which you may want to give to some authorized entity, but in case of one way function, you use in some different scenario where no one is able to go in the reverse direction and get the input. Okay, so for this particular statement, this statement is wrong. uh, third statement, secret key is used as a trapdoor information to compute the inverse of a one-way trapdoor function. Okay, this is true, right? The secret key can be used as a trapdoor information because with the help of secret key you can compute back the x of a given y. Okay, and the fourth statement is that choosing separate keys for encryption and authentication is not needed if the correct order of encryption and authentication is chosen to obtain a secure authenticated encryption scheme. So, is this true or false, anyone? Separate keys for encryption and authentication.
It is false.
It is false, right? Because it is always necessary, even if you choose correct order of encryption and authentication, which is of course encrypt then authenticate, that is the correct approach. But even if you choose that correct approach of encrypt and authenticate, and you choose a CPA secure encryption scheme, and you choose a proper strong MAC for authentication, but still you need to choose separate keys which will be generated uniformly at random from the encryption scheme's key space and from the MAC scheme's key space respectively, because otherwise there will be some information leakage. Okay, so it is necessary to have separate keys for both the scheme, encryption and authentication. Okay, so first statement was correct, and secret key is used as trapdoor information to compute inverse of one-way trapdoor function. These two statements are correct. Okay. So let us read the question first. Let Fk be a secure PRP with input of 2n bits and output of 2n bits. Then consider the following encryption scheme over message space 01 to the power n, that is n bit binary string. The key generation algorithm outputs a uniformly random key k, which is also element of this n bit binary string. To encrypt m belonging to 01 to the power n, choose a uniform random string r, again from 01 to the power n, and output a ciphertext c comma r, where c is equal to fk of m concatenated with r. The decryption algorithm, on receiving c comma r, computes m star concatenated with r star as fk inverse of c, and outputs m star if r star is equal to r, else it rejects the ciphertext. Which of the following is or are true about the given construction? Okay, so there is comment about CPA security, CCA security, and ciphertext integrity. So, any comment on that?
It is CPA secure, definitely.
It is CPA secure. Okay. What about other? You had doubt from this question, I guess.
Yes, right.
Okay, you can ask maybe.
No, if we go as what was explained a few minutes back, so then it does not quite it. Then it is why it's then now that as per previous explanation, so if we change the ciphertext, then the decryption will fail.
If we change the ciphertext, then decryption will fail, right?
Then
because there is this check. Also another thing is that the most important thing, so the point is that this encryption scheme is actually CCA secure. Before going to ciphertext integrity, let me just tell that this scheme is CCA secure. Why? Because F is a secure PRP here. So your randomness is so how the encryption is being done? Yeah, how the encryption is being done? That ciphertext is C comma R, where C is FK of M concatenated with R, where R is the randomness chosen every time independently whenever you are encrypting message M, right? So this scheme is certainly randomized encryption scheme, so it is CPA secure. And about CCA security, my point is that even if you change C to some C dash, because F is a secure PRP, if you remember from the definition of PRP, a small change in the input leads to a huge change in the output actually. So even if X and X dash may be related or may be differing just by one bit, but Y and Y dash, because they are pseudo random permutation, right? So Y and Y dash will seem like a uniformly distributed element over the output space. They will have no relation according to X and X dash. Similarly, according to some M concatenated with R and some M dash concatenated with R dash, although they may have some relation between them, whenever we map apply the function fk upon them, they will be completely independent value, mapping to completely independent value. So if you are trying to go in the reverse direction by changing the ciphertext, let's say C is the challenge ciphertext, encrypting some M0 or M1, okay, that we don't know. So what we essentially try in CCA security game, we try to exploit the decryption oracle. How? We change the challenge ciphertext to some another ciphertext C dash, and then what will happen? So basically, when we apply FK inverse on C and when we apply FK inverse on C dash, similarly, although C and C dash can have some relation, they will certainly map to a valid input, because this is a PRP. So for all possible value of ciphertext, even if it is you are tweaking C to some C dash, but it will map to some value, some input value, but they will not certainly be related to each other. That is why we cannot exploit the decryption oracle to know information about the underlying message bit, message string MB. Okay, so that is how the CCA security is ensured by the security of this PRPF. And then maybe you can similarly argue the ciphertext integrity. So in ciphertext integrity, you essentially want to output some other C dash R dash such that they are valid. They have to be a valid ciphertext, and they have to decrypt to a valid message, right, which is unseen. Okay, now validity will be failed, like as I said that FK inverse will always map to some value of M dash and R dash, but then decryption will fail here because of this check R dash and R. So notice that C is the encryption of M, not of M dash R. Okay, unlike previous case where I said that C is encryption of M concatenated with T, encryption scheme itself was being applied on this message string, which is M concatenated with T. This is the whole message for with respect to encryption scheme, but here message is M only. Now this check is valid when you are checking whether R star is equal to R or not. Failing that check will fail the ciphertext integrity game in this case. So here, yes, it will provide ciphertext integrity and it is CPA secure and CCA secure. Now let me know if any confusion is there.
ma'am, understood.
Understood. Okay. Okay. Thanks. Okay. So these two are correct option. Q3. Select the incorrect options. The goal of the sender and the receiver in the key exchange problem is to agree upon a random common key over a public channel. This is true, right? I
Yes,
think
ma'am. It is
yes.
true.
Yes, thank you. It is true. In the padding oracle attack, adversary can learn the length and value of the padding bytes only. Is it true or false?
Ma'am, it is false.
Right, because it's not the only padding bytes, but also the message bytes also can be learned from padding oracle attack, right? So this is false. Yes. The goal of the sender and receiver in the key exchange problem is to agree upon a fixed common key over a private channel. Of course, this is wrong.
Yes, ma'am, this is false.
Okay. The authenticate then encrypt approach, which is instantiated with a CPA secure encryption scheme and an SCMA secure MAC, is COA secure as well as CCA secure. What about
Ma'am, this is false.
this? Is false because this is authenticate then encrypt approach, which we already know that the final encryption scheme, if it is just CPA secure, that we saw about the padding oracle attack, right? That this does not essentially lead to a authenticated encryption scheme, right? So CCA security will not be there in that case. Okay, so this is done. 3 statements were incorrect, only first statement was correct. So a cyclic group has exactly one generator. Is it true?
No, ma'am, it is false.
False, right? It can have more than one generator. Group Z5 with respect to operation addition modulo 5 has 4 generators. What about this?
This is true.
This is true, right? Because this is indeed a cyclic group and it has prime order, right? The number of elements in this group is 5. So this is a prime order group, and for a prime order group we know that the all the elements except the identity element are actually generators. So in this group Z5 consisting of the elements 0, 1, 2, 3, 4, all the elements except 0 are generated actually. Okay. The order of the group ZP star with respect to multiplication modulo P, where P is prime, is a prime number. So it's saying the order of this group is a prime number. Is it true?
No, ma'am, it is false.
Why?
Ma'am, because it is not a prime number.
Right. So the order of the group is actually P minus 1. So P is prime, but P minus 1 is not prime. So this is not a prime number. And what about the last one? Anyone solved it? (46 to the power 51 modulo 55).
Ma'am, such type of questions were not given in the
Yes,
slide.
I understand that, but
This is
I
the remainder theorem, and we do
yeah,
not taught this remainder theorem.
I also don't know why they were there in the NPTEL website, but it was there. So let me just discuss the solution.
Okay.
So we need to compute 46 to the power 51 mod 55. Now the procedure is basically the final modulo you divide it into prime factorization. So 5 and 11 are two factors of 55 which are co-prime to each other. Okay, 5 and 11 are co-prime to each other. Now you observe that 46 mod 5 is 1, right? And 46 mod 11, that is 2. right? Now in other words, I can write 46 is congruent to 1 modulo 5, just another way of writing. And now you can raise both sides to power 51. Okay, mod 5. So this is 46 to the power 51 is 1 mod 5. Is this part clear? The left hand side.
Yes, ma'am.
Now in the right hand side, what we do is that this also we can write that 46 is congruent to 2 mod 11. Okay, so what we want to compute is that 46 to the power 51 will be 2 power 51 mod 11. Now note that there is this Fermat's little theorem which says that if p is a prime number, then a to the power p minus 1 is congruent to 1 modulo p, where a is co-prime to p. So if p is prime actually, then all the numbers smaller than p, that is 0 to p minus rather I should say actually co-prime to p. So for all the numbers 1 to p minus 1, they are actually co-prime to p, right? So any number from that set, let's say a is a number which is co-prime to p, so a raised to the power p minus 1 is congruent to 1 modulo p. This is Fermat's little theorem. Now considering the modulo 11 space, 2 is co-prime to 11. So using Fermat's little theorem, we can write 2 to the power 11 minus 1 is actually 1 congruent to 1 modulo 11. So that gives us 2 to the power 10 is actually congruent to mod 11. Now we use this 2 to the power 10 is congruent to 1 mod 11. Here we have written 2 to the power 51, so we can write this as 2 to the power 50 into 2, right? It is 51, so I am breaking into 50 plus 1, that is 2 power 1. Okay, mod 11. And this part 2 to the power 50, because 2 to the power 10 is congruent to 1 mod 11, so 2 to the power 50 is this raised to power 5, right? So 1 to the power 5, that is also mod mod 11, right? So 46 to the power 51 is, this is 1, remaining is 2 mod 11. Okay, now you have 46 to the power 51 is 1 mod 5, 46 to the power 51 is 2 mod 11. Now you have to solve for so basically what do you want to solve? So in Chinese remainder theorem, we actually solve the linear congruences like that x is say congruent to 1 modulo m1 and x congruent to a2 modulo m2. Then we want to find out some a such that x is congruent to a modulo m1 m2, right? So here also you will find that. So this is about Chinese remainder theorem. Okay, so you can see on your own. This is not part of foundations of cryptography, this is part of say computational number theory or something, so you can find it there. So Chinese remainder theorem, there you can find how to solve this kind of congruences. So for this particular case you can actually see, so this I can write just x. Okay, now if you solve these two equation, equation with Chinese remainder theorem, you will, I think you will get 46 was the answer, I think. Yes, you will get 46 actually. So basically what so here you for this equation you compute the value of, so this is a1, right, and this is m1, let's say. So here you compute some n1, which is nothing but m1 m2 by m1. Actually, if there are more, here there are two equations, and if there are more, you can get product of all these in the above, and in the denominator you keep the modulus m1 here. So this n1 is 11, and this, then you compute u1, which is 11 inverse modulo 5, right? Now 11 inverse modulo 5 is nothing but 1 modulo 5, because 11 mod 5 is 5, and 11 mod 5 is 1, and 1 into 1 gives you 1, so that is the inverse. So u1 is 1 here, and here n1 is actually m1 m2 by m2, which is 55 by 11, that is 5. Now you compute u2, which is 5 inverse mod 11, and this you can see that 5 into 2 is 10, 5 into 3 15, 5 into 4 20, okay, 9. So 5 into 9 is 45. 45 mod 11 is 1, right? So 5 inverse is 9 modulo 11. Now the formula is that your x will be actually your final result will be actually this a1 into n1 into u1 plus a2 n2 u2 mod 55. So a1 is 1, n1 is 11, u1 is 1, this is 11, plus a2 is 2, n2 is 5, and u2 is 9. So this makes 90 and 11, that is 101 mod 55, which is 46, right? So this is your answer. So this is quite deviating from the actual crux of this course, but this question was there, so I just discussed. Okay, that's it. Next question. Consider the composition of encryption schemes and tag generation schemes and select the incorrect options. Encrypt then authenticate approach leads to an authenticated encryption scheme. This is, you can quickly answer maybe.
Ma'am, this is true.
This is true, okay. Second one, encrypt and authenticate composition may not always lead to authenticated encryption scheme. This is
True.
This is true, right. Authenticate then encrypt always leads to an authenticated encryption scheme.
Ma'am, this is false.
This is false. Encrypt then authenticate approach does not lead to an authenticated encryption scheme. This is false.
Yes, ma'am.
Okay. Okay, so this is done. Okay. Which of the following is or are true? Hardness of the discrete log problem, CDH problem and DDH problem is in the following order. So the order is given. So maybe you can just take a minute of time and then answer. So first statement is about the hardness of the problem. Second statement is about the strength of the assumptions, discrete log assumption, computational Diffie-Hellman assumption, and decision Diffie-Hellman assumption. And then okay, let me first uh, hear your answer for first two statements, and then we go to the last two statements. So what about the order of hardness for this problem and order of strength of these assumptions?
Ma'am, first
Yes.
should be reverse. DDH decisional Diffie-Hellman should be is harder as compared to CDH as compared to D-log.
Okay.
Uh,
Hmm.
Basically, um, I'm actually confused between the first and the second because the strength of assumption, the second option is true.
Okay.
So the first option should also be false then.
Actually, both are true because there is a difference between hardness of problem and strength of assumption. So that is why this question is given actually. Okay, so maybe I can just discuss them. So it is of course discussed in the lecture also, so you can follow from the lecture once again, but let me just discuss here once. So point is that three problems we are talking about here, right? So let me just recall. So in the discrete log assumption we say that the challenger chooses some alpha from the space ZQ. I'm just roughly writing this, and sends to adversary the value of g to the power alpha. Of course, adversary knows the group description, that is the set G, the defined operation on the group, the size of the group, and the generator of the group. They are public information about the group which is known to the adversary. Now adversary gets to see g to the power alpha and it has to respond with some alpha dash, and it wins if it is able to correctly guess the value of alpha dash if alpha dash is equal to alpha. And we say that this for a group where discrete log assumption holds, there the probability that the adversary wins is negligible. Okay, so discrete log problem is assumed to hard in that group. Okay, and the CDH problem is that uh, the challenger chooses randomly alpha and beta, right? Sends g to the power alpha and g to the power beta to the adversary, and adversary's job is to come up with the correct value. So it comes up with some value and it wins if z is equal to g to the power alpha beta. So its job is to compute the value of g to the power alpha beta. Here the adversary's job is to compute the discrete log of this value. Okay, and in the DDH case, the challenger again chooses alpha, beta, and also chooses some gamma, right? Now it chooses it tosses a coin. Depending on whether b is 0 or b is 1, it either sends the tuple uh, g to the power alpha, g to the power beta, g to the power alpha beta, or either it sends this, say for b equal to 0, or if b is 1 then it sends g to the power alpha, g to the power beta, and gamma, which is a random group element. And adversary's job is to tell which one it is seeing. Is it seeing a DDH tuple or is it seeing a random triplet from the group? Okay, So it responds with some b dash and wins if b dash is equal to b. These are the three cases, right? D log, CDH and DDH. Now what is the problem? In discrete log problem, the problem is to compute discrete log of the value g to the power alpha. That is the problem. Now assume that discrete log is broken. Discrete log problem can be solved for a group. Just assume. If discrete log problem can be solved in a group, then that will imply that CDH problem also can be solved for that group. Why? Because if by seeing g to the power alpha you can determine alpha, that is the discrete log problem, right? If discrete log problem is solved, that is the adversary is able to compute alpha from g to the power alpha. Similarly, it can compute beta from g to the power beta. And if it is able to compute both of the value, then on its own it can compute g to the power alpha beta. That is the CDH problem, right? CDH problem asks that given g to the power alpha and g to the power beta, compute the value of g to the power alpha beta. That is computational Diffie-Hellman problem. If discrete log problem can be solved for a group, then CDH problem also can be solved for a group. But what about the other way around? Okay, so this is clearly that let's say that discrete log problem is hard in a group, then is there a way of computing this solving the CDH problem? That is not known. Okay, so it is assumed that discrete log is a harder problem than the CDH problem. So by the hardness of problem, discrete log has more hardness than CDH. Why? Because whenever you have a solution for D log, you have a solution for CDH. But if you have not a solution for D log, then also there could be some other way with which you can compute g to the power alpha beta without computing the individual value of alpha and beta. You may be able to compute g to the power alpha beta. That is not known, but it is assumed that for various groups discrete log problem is even harder to solve. But if you have the solution for this problem, then you have the solution for CDH problem, and if you have the solution for CDH problem, then definitely you have the solution for DDH problem. How? In DDH problem you have to distinguish between these two cases, whether the last value of the triplet is the value of g to the power alpha beta or a random group element of g. So if you are able to compute g to the power alpha beta, that is solving the CDH problem, then of course you can compute the value g to the power alpha beta and check whether the last value is equal to that or not, to distinguish between the two cases. Then DDH will be solved. But there are instances of such group where DDH can be solved but CDH cannot be. So you can distinguish between the two cases by some mechanism, but you can't actually compute the value of g to the power alpha beta. That is why CDH problem is a harder problem than DDH problem. Intuitively you can think in this way, that in DDH you are asked to just distinguish between the two cases, but in CDH you have to compute the exact value of g to the power alpha beta. In DDH you may not know the exact value of g to the power alpha beta, but by some other mechanism you are able to distinguish the value you are seeing, whether it is g to the power alpha beta or not. But you are not asked to compute the exact value. Okay, between D log and CDH also, here you may be able to come up with some mechanism to compute g to the power alpha beta without individually computing the value of alpha and beta. So D log problem, discrete log problem, is a harder problem than computational Diffie-Hellman problem, and computational Diffie-Hellman problem is a harder problem than DDH problem. So this statement is correct. Okay, the first statement is correct, but the second statement, this is also correct. Why? So when we say that we are building a crypto system upon a stronger assumption, that means you are assuming that a easy problem is hard to solve. So when we say that we are building a system on DDH assumption, that means we assume that DDH problem is hard to solve. This is our assumption. Now we know that actually discrete log is the hardest problem to solve among these three. Discrete log is hardest problem to solve, that we know. Compared to that, DDH problem is easier to solve. Okay, but our crypto system relies on the fact that DDH problem is hard to solve. So we are building our crypto system relying upon the fact that a easier problem is hard to solve, easier from some other problem, but our assumption then becomes more stronger. So our intention ideally should be to build crypto system from a weaker assumption, where the assumption is not upon the fact that an easy problem is hard to solve. We want to assume that a harder problem is hard to solve. That is more robust crypto system. But for the sake of implementation, we sometimes, to get a provable security, we just rely upon the fact that a easier problem is hard to solve. So if our crypto system is building upon the assumption that DDH problem is hard to solve, then this assumption is a stronger assumption. So I don't know how much I am clear, but let me know if there is some confusion. So problem wise, discrete log is the hardest problem, but the assumption that discrete log is hard to solve, that is a weak assumption. Let me know if this makes sense. I can try to give some analogy. Let's say you have bricks. Okay, you are building up some construction. Okay, just rough example I am saying. So you have bricks of two company A and company B. Okay, you are using those bricks to build up a wall. Okay, now you know that company A provides a better quality of bricks than company B. Okay, that is known to you. But if still you are using the bricks from company B to build your wall, that makes you are making an assumption that brick B will be long lasting enough to keep your wall standing for next 5 years. Okay, so although you know that bricks from company B are weaker than bricks from company A, still you are using bricks B for building your wall. Let's say that cost you less. Okay, company B gives you bricks in lesser price, so you are building your wall using the bricks from company B, although you know that bricks from company B are weaker than bricks from company A, but your assumption is stronger here, that you are making a strong assumption that bricks B will be long lasting enough to keep your wall standing for 5 years. That is a stronger assumption. Does that make sense?
Yes, ma'am.
Okay, so that is why your first two options are actually correct. Coming to third statement, it says that CDH assumption is true in a candidate group implies that DDH assumption is true in that group. So I already discussed that CDH assumption, actually the next statement, CDH problem is easy in a candidate group implies that DDH problem is easy in that group. So last statement is correct. Okay, not the third one. Okay, So coming to problem 2, given description of a group G, so G is the set, dot is the operation on that group, Q is the size of the group, and G is the small g is the generator of the group capital G. Two random elements are given, alpha and beta. Which of the following may represent Diffie-Hellman function? So let me just tell you that consider both the cases where the group is an additive group and the group is a multiplicative group. Usually when we are talking about this DDH, CDH, discrete log and all, we are actually assuming multiplicative group because we are using the notation like g to the power alpha, g to the power beta. But answer these questions keeping in mind both the cases for additive and for multiplicative group. So take 1 minute of time and let me know which are the correct answers among them. Anyone? For the multiplicative case it is easy, right?
For the multiplicative case, third option is correct.
Correct. And for the additive case?
Additive case. The fourth option.
Right.
None.
Right. Fourth option is correct. You were correct. Yeah. So
Can you explain the fourth option once?
yes, I will explain both actually. So basically Diffie-Hellman function of alpha comma beta. So the third one actually, like, this is how the function is defined, what to say. So usually by notation, so maybe you have seen in this manner. Let me write in this way. When we say that the challenger has chosen alpha, okay, from ZQ is multiplicative group. Okay. I should write G actually. Okay, sorry. I should write G. Some group G. And then it computes U equal to G to the power alpha, V equal to G to the power beta. And then Diffie-Hellman of U comma V is given as G to the power alpha beta. Yes?
Ma'am, I don't think so. Alpha belongs to group G. Alpha belongs to the ZQ. ZQ. Because alpha is that random number raised to the power of, that will be raised to the power of G.
Right. You are correct actually. Right. Thank you. G is the generator element from the group G, and this actually any element between 0 to q minus 1, because there are cube elements, so G to the power that should give a valid element in the group. Yes, you are correct. Okay. Then we have seen the Diffie-Hellman function to be written as this, that dh of u comma v is G to the power alpha beta. So here it is written just in some tweaked manner, where it is saying that dh of alpha and beta. So you basically need to write G to the power, here alpha is d log of u. So here actually you have to write G of discrete log of alpha and discrete log of beta. That's it for the third option. And for the additive case, actually what you should write, so again alpha is chosen from ZQ and U then is computed as alpha into G, because for additive group it is like g plus g dot 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 g alpha times, right? In case of multiplicative group, it is g multiplication, like this, like the operation dot, if it is multiplication, then it becomes alpha time multiplying g, which is g to the power alpha. But if this dot operation is actually addition operation, then adding up alpha times g gives you alpha into g actually. Okay, so similarly beta into g for another beta. And then Diffie-Hellman of alpha comma beta is nothing but, I mean, okay, Diffie-Hellman of u comma v is actually alpha plus beta into g, right? So that is why, so plus is nothing but the group operation here, you can understand that this is group operation, whatever operation is this. So similarly for additive group, that's why I am writing that dh of alpha beta is discrete log of alpha, group operation discrete log of beta into g. Okay.
Ma'am, here in the question it's not mentioned it's a multiplicative or additive or both.
It is not mentioned, that is why the multiple option correct.
We need to see all possible options.
It is saying that may represent, right? So
And ma'am, I had one question. When we say d log in case of additive operation, so it's going to be like if we say u is equal to alpha into g, then in case if we have to find the d log of alpha, then it will be u into g inverse.
right. If right, you are, so where is it? U is alpha into g, and I am saying to find the discrete log of u, then it is alpha in I mean, sorry, you apply u g inverse is alpha, right? So you compute
Yes,
u
so
g.
alpha is the d log of alpha.
Alpha is the d log of u here.
D log of u, yes.
Hmm.
Mm.
Okay. Let G be a prime order cyclic group of order Q with a generator G. Let H is a hash function from G to K modeled as random oracle. Which of the following problems should be difficult to solve in G, so that the probability distribution of g to the power alpha, g to the power beta, and h of g to the power alpha beta is computationally indistinguishable from the distribution of g to the power alpha, g to the power beta, and r, where alpha beta are randomly chosen from zq and r is randomly selected from k. So I can wait for your answer. Anyone? Okay, so let's proceed one after another. What if discrete log is not hard to solve in G? Then does this two distribution remain indistinguishable? So the two distribution is given g to the power alpha, g to the power beta. Sorry. beta.
And what does probability distribution mean here? Does it mean that the end user knows G alpha, G beta, and H of G alpha
Yes,
beta?
it can see uh, distribution means basically it maybe some polynomial number of samples either of this form or of this second form are available to some adversary, and the adversary will tell which kind of sample it is seeing, the first kind of or the second kind of sample.
Okay. Okay.
So what if discrete log is not hard? Then can it, by looking at this particular sample which can have this form or this form, it can tell whether it is seeing the type 1 or type 2 sample if discrete log is not hard.
Yes.
It can tell, right?
Yes.
Because it is seeing any so basically g to the power alpha and g to the power beta is visible in both the cases, so it can compute alpha and beta from that if discrete log is not hard. And then what it can do, it can compute g to the power alpha beta on its own and apply the hash function also. Hash function is a function modeled as random oracle, so it can query the random oracle with g to the power alpha beta and get to know the value of h of g to the power alpha beta, and then it can simply check whether that value returned by random oracle is equal to this third component or not. If it is equal to third component, then it is seeing type 1 sample, otherwise it is seeing type 2 sample, correct? So discrete log needs to be hard. Okay, so which of the following problems should be difficult to solve in G so that these two remains indistinguishable? So for indistinguishability of these two, we need discrete log to be hard. This is correct. What about computational Diffie-Hellman? Do we need this to be hard so that they remain indistinguishable or not? So let's assume CDH is not hard. You are able to solve CDH problem. Then are you able to distinguish between them?
Yes.
You can, right? How?
Mm. Because we know G alpha, we know G beta, G raised to the beta. Then
Then by if computational Diffie-Hellman is not hard, then basically from that information, from the information of g to the power alpha and g to the power beta, you are
we
able
can
to compute g to the power alpha beta, and then
we
you,
can we
yes,
can basically, it means we can find alpha beta, and
not
then we
not
can,
necessary. We can find alpha beta if discrete log is not hard, but
yes,
forget about discrete log now. Now just assume that CDH problem is solvable. If CDH problem is solvable, that implies that from g to the power alpha and g to the power beta, you can directly compute g to the power alpha beta by some means not known. Somehow you are able to compute g to the power alpha beta directly if CDH is not hard. Then once you know g to the power alpha beta, you can query the
mm,
random oracle with g to the power alpha beta and see the value of h of g to the power alpha beta, and then check again the third component whether it is equal to the third component of your sample or not, and you are able to distinguish. So to keep these two distribution indistinguishable, you need CDH problem to be hard. So this is also necessary. What about DDH, decisional Diffie-Hellman? So if decisional Diffie-Hellman is easy in a group, does that help here to distinguish between these two distributions?
yes,
How?
because then it will be able to distinguish between an element from group and a random element from the set K.
But the point here is, uh, by decisional Diffie-Hellman, you can distinguish between g to the power alpha, g to the power beta, g to the power alpha beta, and g to the power alpha, g to the power beta, and some random r from group.
Hmm. Hmm.
But here there is another h applied on g to the power alpha beta. So
Oh, what? Okay, okay. I
that is the
forgot
catch.
that.
Yeah.
That I forgot this.
So DDH being hard does not give you extra advantage to distinguish between these two cases actually, h of g to the power alpha beta and r. Okay, so DDH need not be hard in the group to keep them indistinguishable from each other. These two needs to be hard actually. So as I said, DDH is a easier problem. Even if DDH is solvable, you can distinguish between g to the power alpha beta and some random element of g. But here you have to distinguish between h of g to the power alpha beta and a random element from k, that is the output space of h. So DDH becoming easy does not help necessarily. So first two options are actually correct. This is again easy question. We want to build a PRG, pseudo-random generator, F, from ZQ square to GQ, where G is a prime order cyclic group of order Q with a generator G, where D log CDH DDH assumptions hold. So we assume all these three problems are hard to solve in group G. Let f of alpha comma beta is equal to g to the power alpha comma g to the power beta comma x. For what values of x the function f is not a PRG? Do you remember PRG? How many of you remember PRG? Let me know. Pseudo random generator. What is the security property for pseudo random generator? Yes? Anyone? No? So, what is the input to a PRG?
A key.
Do we call it a key? We call it a seed,
Seed,
right?
yes. Seed.
So it is a seed. So for pseudo-random generator, the seed is secret, okay, and we generate a bit stream, and that bit stream is supposed to be indistinguishable from a uniform random bit stream, okay. That is the concept of PRG, pseudo-random generator. Now you are defining a PRG in this manner, where seed is alpha and beta both, so you may consider is just alpha concatenated with beta, and your output of the PRG is defined as g to the power alpha. So I can, let me write it as, the seed is, let's say, alpha concatenated with beta, and the output is g to the power alpha, then g to the power beta, and then x. Now you have to tell that for which value of x this string is not indistinguishable from a uniform random string. These things you can just try replacing. So okay, let me try one after another. So if I write the pseudo random string as g to the power alpha, g to the power beta, replace x with g to the power alpha plus beta. If this is the output of my pseudo random generator, is it distinguishable from random string by a polynomial time adversary? Can I distinguish this string from the pseudo random string?
Yes.
How?
Because we know alpha, we know beta. So we can calculate G alpha, G raised to alpha, G raised to alpha, beta, and
We don't know alpha and beta. This is seed.
but that is the input to
This is input to PRG, but that seed is not,
which is
if you
known.
remember the concept of PRG, the seed is not known to adversary. If you know the
Yes,
seed, if you, of course you can see the output of PRG, and you can run the PRG on your own. it,
yes,
that's not the case. So adversary does not know the value of seed. It just sees the output of the PRG, and it has to distinguish whether this output is distinguishable from a truly random string. So let's say the output string has this format: g to the power alpha concatenated with g to the power beta concatenated with g to the power alpha plus beta. If this is the format of the string, does it is it distinguishable from a uniform random string?
no, then it is no.
Okay, let me tell you, it is distinguishable. How? So first component you can see, second component you can see, third component you can see. What you will check? So remember the game of PRG, the challenger just outputs g of s, right, to adversary. The adversary somehow has to exploit the format of output string to distinguish between g of s and a truly random string. What in this case the adversary can do? Adversary can take the first part, it can take the second part, multiply
And
them,
multiply.
and check
Yes,
whether it is equal to the third part or not.
yeah,
That is how
right.
that is the strategy of the adversary to differentiate it from the uniform random string. So this will not be a PRG for this, so it is a correct answer. And now quickly you can tell, if I replace this with g to the power alpha, what happens? The x part is g to the power alpha,
Then again, it is distinguishable.
right, it can just check the first part and third part whether they are equal or not, and answer accordingly. So this cannot be the case. This also cannot be the case for the same reason. What about this? G to the power alpha beta. Now what happens? This is now
This is indistinguishable.
this is indistinguishable because for group G, DDH assumption holds. So by DDH assumption, because g to the power alpha beta is indistinguishable from a random group element, so this remains indistinguishable from a random string. So for this only it remains a PRG output, otherwise it is not. So the question asked for what value of x the function f is not a PRG. So for all these three cases it is not a PRG. Okay. This is a trivial kind of question. Let me read it out. Assume two parties P1 and P2 who are taking part in an instantiation of Diffie-Hellman key exchange protocol. They use an additive group G with generator small g and binary operator dot. Which of the following statements is or are correct? P1 chooses random element R1 from G and sends R1G equal to applying G R1 times, right, to P2. Okay, I think again this should not be G, this should be the size of the ZQ as you said. Anyway, okay. Okay, so let me write. So P1 chooses random element R1, and there is P1, there is P2. P1 is sending R1G to P2. P2 chooses random element R2 and sends R2G to P1. P1, after receiving some value alpha from P2, So here P1 is receiving R1G, right? So alpha is R1G, let's assume. P1 after receiving some value alpha from P2 computes the key K equal to R into alpha, where R is some random element chosen by P1 in the previous step. So in the previous step P1 actually chose R1, right? So R is R1 here, and it computes K equal to R alpha. So R is R1 that was chosen by P1 itself in the previous step, and alpha is R1G that is sent to R2G that is received from P2, right? P1 after receiving some value alpha from P2, so from P2 it received R2G, so R1 into R2G, that is the key K according to the third statement. And according to the fourth statement, P1 after sending some value beta to P2, so P1 is sending R1G to P2, computes the key K equal to R beta, where R is some random element chosen by P1 in previous step. So P1 chose R1 in the previous step, so R is R1 and beta is actually R1G. So according to the fourth statement, P1's key is R1 into R1G. So which among them are correct actually?
And first two steps are the process, right?
They were statement also, but like it is like if you think that they are not proper, then like they are given a statement only, you have to decide whether they are correct or incorrect. But I think the way I wrote it, it already became like a process, which is like they are in fact correct, first two statements,
Yes.
because this is true for a additive group. The way we have written it, we are used to write as g to the power r1, g to the power r2. So basically what happens, one party chooses some random element, it computes the value of g to the power alpha or alpha into g depending on multiplicative or additive group, and sends it to the another party, and another party also does the same from his or her end. So yes, first two statements are correct. And then for the next part, to convert on a particular key by both of the parties, so at the end of the key exchange protocol both the parties should have a common random key, right? Now what will be the common random key? So it's already obvious, I think. Third or fourth statement, which one is correct?
The third statement is correct.
Yeah, third statement is correct, because then only your key is r1 r2g, and p2 also then like in the similar manner p2 can also do this thing, that it receives r1g from p1 and it multiplies to it its own random choice, so that both of them agree upon r1 r2g. But according to the fourth statement, on the p1 side the key becomes r1 square g, and on p2 side it will become r2 square g, which are never equal, and this cannot be a valid protocol. So yes, third statement is correct, first two are also correct. Which of the following are limitations of Diffie-Hellman key exchange protocol? The algorithm outputs any uniformly random element from the key space. So the question is, which of the following are limitations of Diffie-Hellman key exchange protocol? Okay. Limitations of Diffie-Hellman key exchange protocol. The protocol requires both the parties to remain online during key exchange. The protocol does not provide security against active adversary. The protocol cannot be used in practice in its absolute form. The output of the algorithm is uniformly random group element.
first statement is incorrect. It's
First
not a
statement
limit.
is incorrect, but yes, it is not a limitation of, like, it is incorrect. It does not at all apply to differential key exchange. So, and the last statement is correct, but it is that is also a limitation actually, because it does not return a uniform random bit string. It returns a uniform random group element, so we need to modify the scheme, like applying some key derivation function or something. The second statement says that both party requires to be online during key exchange. This is also true, and this is the limitation of differential key exchange. The protocol does not provide security against active adversary. This is also true, and also a limitation. The protocol cannot be used in practice in its absolute form. That is also true, and that's why it needs modification accordingly, so that it can be used in its in practice. So limitations are, yes, both party needs to be online, does not provide active security, cannot be used in.
How is the last one? How is the last one the limitation? It's a uniformly random group.
Limitation because it's a uniform random group element, not uniform random bit string from some n bit length string. So you need to apply some, you get a uniform random thing from a group G, but then you have to map that to some uniform random string over some bit length space, right, using some key derivation function or something. Then it is usable in practice.
It's more like an extension. Then it needs an extension.
It needs some extension, otherwise you cannot use it in practice. So that is why it is a limitation. Match the left column with right column such that group in the left column satisfies the assumption in the right column. Assume P to be sufficiently large and choose the strongest assumption if there are more than one matches. Let me know your answers. ZP star with multiplication modulo P. Is this group a valid group where D log CDH DDH holds? Not necessarily, right? In fact, ZP star does not have a prime order. So discrete log is not necessarily hard, right? For additive group ZP with addition modulo P, there actually discrete log is easy to solve. For prime order cyclic subgroup of ZP star and this multiplication modulo P, so you have already seen, right, that for two primes P and Q such that P is of the form R into Q plus 1, okay, then the subgroup of order Q, like subgroup of ZP of order Q with this property satisfied, that P is equal to RQ plus 1, that prime order cyclic subgroup with sufficiently large value of prime p actually there holds all these three assumptions, discrete log CDH and DDH, and as it is saying that strongest assumption needs to be choose, so strongest assumption, as I already discussed, that DDH assumption is the strongest assumption. So C maps to 2, and any cyclic prime modulo elliptic curve with point addition. So basically cyclic prime modulo elliptic curve are used where DDH assumption holds true, but not any cyclic prime modulo elliptic curve. There are restrictions where these although the elliptic curves are prime modulo and cyclic and all, but still they cannot be used because their DDH is broken. So examples are given in the lectures, actually we will come to that. So not any, the statement any actually makes it invalid, and so we cannot say any cyclic prime modulo elliptic curve with point addition holds these assumptions true. So the final answer is A maps to 4. Okay, so basically in ZP star discrete log holds true, but not the other assumptions like CDH, DDH and all. And so and B maps to 1, as discrete log also solvable there. Prime order cyclic subgroup, there it maps to 2 strongest assumption, DDH assumption, and for D it goes to 1 because any cyclic group is not the correct statement. Okay, this also can be answered directly. Choose the incorrect statements. A cyclic subgroup of ZP star with multiplication modulo P with P equal to RQ plus 1, where both P and Q are prime, having the form G equal to H to the power R mod P, where H belongs to ZP star, has order Q. A cyclic subgroup of ZP star multiplication modulo P with P equal to RQ plus 1, where both P and Q are prime, having the form G equal to H to the power R mod P with H belonging to ZP star, has a total of Q minus 1 generators. Okay, and DDH assumption holds true for a prime order cyclic subgroup of ZP star with multiplication modulo P such that P is RQ plus 1, where both P and Q are prime, having the form G equal to H to the power R mod P, H belonging to ZP star, if the bit length of P is greater or equal to 2048. Is there any statement which is incorrect here? Any incorrect statement among these three, anyone? Basically all three are actually correct, because so in the lecture, as it has been discussed that for a cyclic subgroup of this form, right, they actually are group where DDH assumption holds true, and the group has order Q such that Q satisfies this condition, P equal to RQ plus 1, and Q is a prime. So as you know, for a cyclic prime order group, all the elements in the group except the identity element are generators of the group. So Q is a prime and the subgroup is a cyclic subgroup and so all the q minus 1 elements of that group will be generated of the group except the identity element, which is 1 for multiplicative group. So first two statements are correct, and for the third statement, yes, DDH assumption holds true not for any prime order cyclic subgroup of ZP star multiplication modulo P with P equal to RQ plus 1, but for large enough P. For practical instantiation of a system where DDH problem is hard to solve, for that we need the bit length of prime P. So if you represent the prime P in binary string, whatever is the bit length of P, that we represent here inside this modulo bracket, right? So that bit length of P should be greater or equal to 2048 in order to have a group where DDH assumption holds true. So basically none of the above is the incorrect statement. Actually none of the above are incorrect. Okay. This is a descriptive problem. Determine the points on the elliptic curve E defined as y square equal to x cube plus 2x plus 1 over z11. How many points are there on the curve? You are asked to determine the points on this elliptic curve over z11. This is a prime modulo elliptic curve, right? Also, so you have to basically check which are the points on the elliptic curve. How do we check? I can just discuss this, okay? So how do we determine the points on the elliptic curve? So what you do, you first check which are the elements in Z11 that are perfect square of some element modulo 11. So you first determine the square modulo 11 for all the elements between 0 to 10, right? So in the left hand side you can see y and y square. So for y values of 0 to 10, you compute y square mod 11. For example, 4 square is 16, 16 mod 11 is 5. 5 square is 25, 25 mod 11 is 3. 6 square is 36, modulo 11 is 3. Like that you compute all the y square mod 11 for y belonging to Z11. And you can see that only 0, 1, 3, 4, 5, 9. These 6 elements 0, 1, 3, 4, 5, 9. These 6 elements in Z11 are actually perfect square of some element in Z11. Rest of the elements like 2, 8, these are not present here, so they are not perfect square of some element. So only these elements are perfect square of some element in Z11. Now you compute the value x cube plus 2x plus 1 mod 11 for various values of x. So you go from this direction, x to x cube plus 2x plus 1 mod 11. For example, let's say 4. So 4 cube is 64 plus 2 into 4 is 64 plus 8, 72 plus 1, 73 mod 11, that is 7. So like that you compute all the values of x cube plus 2x plus 1 mod 11 for all values of x in Z11, and then you know that this one, because it is the value of x cube plus 2x plus 1, so that is y square. So for all the values of y for which y square is equal to 1, those will be valid x comma y points, right? So because you have already seen that 1 is a perfect square for y equal to 1 and y equal to 10 also. right? Y equal to 1 and y equal to 10. Both leads to square uh, 1 mod 11. So our x comma y becomes, actually x was 0, so 0 comma 1 and 0 comma 11, because putting 0 here gives you 1, and 1 is, so square root of 1 is 1 or 10. So 0 comma 1 and 0 comma 10 both are points on elliptic curve. Similarly, putting x equal to 1 gives you 4, and 4 is square of both 2 and 9. So 1 comma 2 and 1 comma 9 are points on elliptic curve. In the same manner, you can compute rest of the values, and in this manner you can get 1 2 3 4 5 6 7 8 9 10 11 12 13 16, right? 6 no. 15 points you get like this. And apart from that, always remember there is this point at infinity of an elliptic curve, which is nothing but a point which is assumed to be there as an intersection of all the y-axis, I mean all the y values. So in a graph, usually when we draw a graph, so this is like x equal to 1, x equal to 2, like that, all the vertical lines. Now we assume that all these vertical lines meet somewhere at the infinity, and that point we call point at infinity for an elliptic curve. So that is the identity element of the elliptic curve with point addition operation. So all these points computed like this manner, and then the point at infinity together forms the set of points in elliptic curve. Is this clear? There was nothing like
Yes, ma'am.
explaining anything. Okay. Choose the incorrect options. Given a point P on an elliptic curve and O, the point at infinity, P plus O is equal to P. Next option says if P is equal to x1 comma y1 and Q is x2 comma y2 are two distinct points on an elliptic curve, and lambda is the slope of the line connecting P and Q, then P plus Q equal to x3 comma y3, where x3 is lambda square minus x1 minus x2 and y3 is lambda into x1 minus x3 minus y1. Okay, going one after another. First statement is correct or not?
Yes, ma'am.
It is correct. Just now I said that point at infinity is the identity element of an elliptic curve with point addition. So whenever a point is added with that identity element, the same point is returned. So first statement is true. What about the second statement? What about the second statement? P and Q are given.
I think I don't remember the formula. I think there was some condition where I think when y1 is equal to y2, then this.
Yeah,
there-
this is actually correct. You are correct that there was some condition, but the main crux is still the same. Actually, this is correct. I will just show the detailed computation in the next slide.
Do we need to remember these formulas, this derivation?
This is related to elliptic curve cryptography, not related to foundations of cryptography, but anyway, if you are learning cryptography, then it is good to it's not like if you are handling it frequently, then you will remember. Nothing very sophisticated. If P is x1 comma y1 is a point on an elliptic curve and Q is its x-axis reflection given by x1 comma minus y1, then p plus q is 0 comma 0. Is it true? Third statement, anyone? Okay, this is not true. Basically x1 comma y1 and x1 comma minus y1, they are inverse element of each other in the elliptic curve group with point addition, and p and q when added up to inverse element, that gives the identity element back. And remember, identity element of the elliptic curve is the point at infinity, not 0 comma 0. So the true statement would be p plus q equal to O, this, not 0 comma 0. So this is wrong. And the last statement says if p equal to x comma y is a point on an elliptic curve, then 2p equal to 2x plus 2x comma 2y. This is wrong. 2p is actually the way you add x comma y and x comma y in elliptic curve. That is not 2x comma 2y. You have the same formula here, right? Like that you will compute, and we'll just briefly see from where this formula comes. So just look at this, that p is x1 comma y1 and q is x2 comma y2, and you want to compute p plus q. So first case was x1 not equal to x2, and there how do we compute the summation of these 2 points? That will be the reflection of the point, that is the straight line going through p and q. Basically any straight line that passes through p and q also intersects the graph in some third point. So it necessarily intersects the graph in 3 points. Among the 3, 2 p and q are given, and the third point, first you compute that, and then you take the reflection of that point as the sum of p and q. So the straight line written as y equal to lambda x plus c intersects the elliptic curve in 3 distinct points. You replace the value of y in elliptic curve equation. So because we are talking about intersection of 2 different graph, one straight line and another the graph for this elliptic curve, so you just put in the elliptic curve equation, in place of y you put lambda x plus c, and then you get this equation. Okay, you just open it up, lambda square x square 2 lambda cx, keep them to same side, and you get this equation. And this equation has 3 roots, right? Let's assume x1, x2 and x3. So x1, x2 are already the 2 known points p and q, and there will be x component of the third point, which we denote as x3. And by the rule of for this solving this degree 3 equation, we know that this particular coefficient lambda square is the sum of all the roots of this equation. So lambda square is equal to x1 plus x2 plus x3. So we can compute the value x3 as lambda square minus x1 minus x2. That is the logic why we write x3 equal to lambda square minus x1 minus x2. And then how do you compute y? For that you need to know the slope of the straight line, that is lambda, and you already know the 2 points on the straight line, x1 y1 and x2 y2. So slope of the straight line is computed as this, y2 minus y1 by x2 minus x1, right? And then you just do this, right? You put y3 in the slope equation. I think this just a minute. What I am saying is that this is how you can you can compute the value of the slope lambda. And then again x3 y3 is another point on the straight line, so you can write y3 minus y1 by x3 minus x1 also as the slope value, and then you put already computed value x3 in the equation and compute the value of y3. So that is how you compute the x3 comma y3 point, and then take the reflection, that is x3 comma minus y3 as the sum of them. And in the second case you already know that for y1 equal to minus y2, this is considered as point at infinity, summation up to inverse point. And in case 3 again x3 is computed in the same manner, right? Lambda square x3 equal to lambda square minus x1 minus x2, because x1 and x2 are same, so you can write lambda square minus 2x1. And for the slope, in the previous case you computed the slope as y2 minus y1 by x2 minus x1, because it was a straight line connecting x1 y1 and x2 y2. But here actually, because x1 and x2 are same and y1 and y2 are also same, so basically p and q are the same point, so you are actually computing 2p, p plus p, right? So the slope of the straight line is the slope of the tangent of at that point p. So slope of tangent at point x1 comma y1, so you can compute this. So you first take derivative of the both side for the equation of elliptic curve, that gives you 2y dy dx equal to 3x square plus a, and this is the slope of the straight line, so you can compute the slope as 2x square plus a by 2y. So by 2y is basically the inverse element of 2y1, so you put the value of x1 and y1 in this equation and compute the slope, and then use the value of the slope to compute the value of y3, and then again take the reflection of that point as the sum of p and q, which is like 2p here. Okay.
Ma'am,
Yes.
I had one question.
Yes.
Uh,
Go ahead. Your
Line
voice,
isn't
sorry, I did not get your voice.
am I audible now?
Yes, now it is okay.
So, ma'am, my question is that in the previous slide, uh, when we are saying yes, in this slide, when we are saying that, I'm sorry. So, in the previous slide, when we are saying that P, Q are the 2 points, and when we say P plus Q is the addition, and it goes to the third point, and the third point of reflection of the third point is what we are looking at. So so the question is now that if I say P plus Q is equal to the third point R, and so then can I say that P plus R is equal to Q?
No, actually p plus q is not equal to r. P plus q is equal to reflection of r. That is how addition is defined. So
Okay. But if I say that in this proceed, okay. So
if you remember from the,
so if I,
yes.
no, if I say then if I add P, if I assume that on the elliptic curve there are 3 points P, Q, and R dash, right? They are on the same line R. So I can say R and P plus Q is equal to R dash is what I would say. So if I say P, Q, and R are the 3 points which are there on the line, then I guess then if I say P plus R, if I say if instead of saying P plus Q is equal to R dash, if I say P plus R is equal to Q dash, then is that what we can also say that?
Okay, let me just. I am also confused what you were exactly trying to say. Let me. So, let's say this was like picture like this, maybe. I
Yes.
don't know, something like that. So, okay, I think there is four. Okay, no. Mm, this is only, let's say.
Yes.
So
So
there
there
are
are
three
three
points.
points.
So this
If
is
if we
P.
mark
q,
Yes.
you were saying this is r.
This is R. Right.
Okay.
So, so if now yes. So we say P plus Q is equal to minus R, right?
Yes.
So can we now say that P plus R is equal to minus of Q?
P plus q is minus r, then p
Can we say
plus,
also that please P plus R is equal to minus Q? That also we can say, right?
yes, we can, because if you see from picture also, if these lines are connecting, uh, I think the drawing is not that good, but yes, the line connecting minus r and minus q goes through,
No,
uh,
basically, uh, yes, P plus R. Well, I'm just talking of that same line that we have drawn
yes, p
previously.
plus r is equal to minus q, right? Because this is the third point on this line, intersecting line,
Yes.
and minus q is the reflection of that. So yes, p plus r is minus q. Yes, that is true.
Ma'am, I'm not able to understand the application or how it will be used. Uh,
For that, you can look at this completely different sector of elliptic curve cryptography, ECC.
yeah.
There are various applications also.
So when we like a different question is that I'm trying to basically appreciate that how it will be used. So when we talking about keys and public key and private key,
Hmm.
so then in that case, this elliptic curves are used for calculation of the keys. Yeah, how is that?
So as you have may have already seen in the lecture, right, that why we like DDH assumption holds true in elliptic curve with point addition for certain elliptic curves, and we prefer to use that instead of using the normal cyclic group, cyclic prime order subgroup of ZP star, right?
Mm-hmm.
The
Mm-hmm.
main
Yes.
reason being that the parameters needed for that case is quite huge. Like in the previous slide only we mentioned that the bit string, the bit length of p should be greater than 2048, which is huge. But uh, opposite, like in contrast to that, in case of elliptic curve, you just deal with the prime p, where p has bit length of say 256. So
Mm-hmm.
with smaller parameters you can work, you can have same amount of security with smaller parameters, so it gives you efficient construction. So that's the motivation for switching to elliptic curve cryptography.
Okay.
I think this is the last question. Let's just quickly take a look at, nothing to explain here also. So let E be an elliptic curve over ZP for some prime P, and consider the cyclic group consisting of the points of E along with the point addition operation. Which of the following cases lead to a group where DDH problem is easy to solve? So those groups are prescribed not to be used for uh, construction where DDH assumption needs to be hold true. Basically, so let me just say that all these three options are correct. For all these three cases, DDH problem is easy to solve. Nothing to explain here, you can just refer to the lectures there. They also did not go into any detail, just mentioned that for this this E inside straight line, this is nothing but the number of points in this elliptic curve. So if that is equal to the prime P, the prime modulo of that elliptic curve, so called as anomalous curves. For that, your DDH problem is easy to solve there. Also super singular curve holding this condition, and also the condition where size of the elliptic curve group divides p to the power k minus 1 for small k. All these cases should be avoided to be from being used as in the construction where DDH assumption needs to be equal to. So basically you have to check not all cyclic prime modulo elliptic curve with point addition are eligible to be used. So yes, that is all. uh, if you have not any more question, then maybe I can stop here. Okay, thank you for joining.
Thank you, ma'am.